back, students. This is going to be the final part of our study of heat of reactions. At this point, you have already done your calorimeter calibration. And remember that we are going to do the following. This is our setup for this particular experiment. We have a styrofoam cup, actually a double styrofoam cup, with a reaction that is happening in solution in water. This is what we call the system. We have a thermometer in there. We're going to measure what is the temperature change in the calorimeter. So let me go back here to our regular document camera and let's review a little bit of this to remember where we came from and where we're headed.
Let's go back to the beginning of our presentation so we can remember what we're doing this for. Remember, our goal, our target is to find what is the enthalpy of this reaction, because that is essentially the enthalpy of formation of a metal oxide. Since we cannot really study that reaction directly, we have applied Hess's law, remember? Hess's law, which says that the total enthalpy of a chemical reaction only depends on the enthalpies of the reactants and the products, regardless of the path. So what we did was we invented this path, and in doing so we were able to essentially break down our target reaction into a set of components that we could arrange conveniently. So what we ended up was using the reactions of a metal with hydrochloric acid and the oxide of the metal with hydrochloric acid, which are reactions we can carry out in our calorimeter. So our goal ultimately is going to be to find what is the enthalpy of those reactions. So we will measure the reaction of the metal with HCl and the reaction of the metal oxide plus HCl. And then we have a third reaction, which is essentially the formation of water, which is a given. We have the value for that one. We said this is minus 285.8 kilojoules per mole. Now remember, again, and don't forget, we're going to have these files available for you in PDFs so you can use them to go along with the presentation. Now remember this other sketch that we did here. We said the chemical reaction is going to take place inside a set of styrofoam cups. Now we just measure the temperature change of the solution, so we never actually measure the temperature change of the reaction itself. Once more, we're going to apply the law of conservation of energy to calculate what is the heat of our particular reaction. And remember that the heat of reaction is going to depend on the heat of our solution, which we measure here, and the heat exchange due to the calorimeter, which we have already calibrated. Let me roll this a little bit to the side here so we can see it, and we can calculate what that is. So what we're going to do is we're going to measure the change in temperature that happens in a solution once we add our metal or our metal oxide, and we're going to use that to calculate ultimately the heat of our reaction. Now, you're going to be given a data sheet. Looks something like this. And if you had the manual, this would be page 39 of the manual. And you'll be provided with a set of data for a metal or a metal oxide, right? And please pay attention to what metal or what metal oxide you have. In the online simulation that we're doing, some of you may receive calcium, some of you may receive data for zinc and of course the corresponding oxides. So make sure that you write down on your data that you copy which one it is, and also on your graphs that you're going to be drawing. So essentially you will start with a given mass of your sample, which you will combine with a specifically measured volume of solution of HCl, and you will have the tracking here of the temperatures again every 30 seconds, and you will use this to build a graph. Let's go to our presentation again, and then we'll come back here and do a sample set of calculations.
All right, so as you can see, you're going to be provided with a data sheet that has values of temperatures read as the reaction progresses. So let's go here to our screen and see how we're going to handle this. Okay, so this is the last part of our experiment and applying Hess's law. And this is what we're going to work with when we do heats of reactions. So our reaction is going to be a reaction between magnesium and HCl. Remember, you may get a different metal. We're going to use magnesium for this particular sample set of calculations. There you see the reaction between magnesium and HCl. And as we said, you're going to start at a certain temperature of your solution of HCl. You're going to promptly add a pre-measured amount of magnesium metal. And then you're going to track what is the temperature change that happens over a space of about 7 minutes, taking the temperature every 30 seconds. Don't forget, it's very important that you continuously swirl or stir the solution to make sure that heat is distributed evenly throughout. That way the thermometer will be actually gathering measurements of the average temperature of the solution. So let's say that we're going to do a graph of this, and this is the graph that we obtain. Once more, don't forget to put a title, to list out or label your axis correctly with the proper units, and make sure you indicate which metal it is that you are tracking here. Now, there is a problem with this particular set of data. Now, notice that one of the things that we do is we see that towards the end of the time period, the reaction tends to start going downwards. That's because, of course, we said the setup we have is not perfect. There is going to be some thermal exchange with the environment. And since the room temperature is actually lower than the temperature generated by the reaction, we're going to lose heat to the surroundings. So what we try to do is we're going to try to do a projection that goes all the way back to the y-axis. Now, there's a problem with this situation here, and it is that data point there. Notice that that initial data point is off of the trend. And so what we do is that we are going to discard that data point. So what we're going to do essentially is, and let me erase this line that I made here. What we're going to do is we're going to use only the data that starts at the higher temperature in the trend. So we're going to discard that data point at 30 seconds, and we're going to run a graph starting at 1 minute. As you can see now, the value of the final temperature, we can get it once more by looking at the equation of the line, and that intercept over there is going to be our highest point, as if this is the highest temperature the system would have caused the solution to reach, right? 38.707 is outside of the precision capabilities of our instruments. Our thermometers can only read to 1 decimal. So we're going to say that our final temperature in this case is rounded to 38.7. Okay, let's go on and let's see how we're going to set up this reaction. So again, our reaction is magnesium with hydrochloric acid. And here's the data that we're going to use for our sample calculations. We're going to have 0.4817 grams of magnesium mixed into, or thrown into, sort of, 100.0 milliliters of 3 molar HCl. We need a little bit of extra data here. For example, we need the density of the solution, that's 1.050 grams per milliliter. We need the specific heat of the HCl solution, that's 4.9166 joules per gram per degree Celsius. This is all given in your handout, actually. I'm just summarizing it here. The heat capacity of the calorimeter in our previous example, we calculated it to be 22 joules per degree Celsius. And according to our data, the initial temperature was 20.5 degrees Celsius, and the final temperature, based on the projection of the trend line towards the y-axis, is 38.7 degrees Celsius. So let's go to our document camera here, and let's work through the calculations using this data.
Let's walk through this sample set of calculations. Notice that we are using a reaction with magnesium. Now you're not going to receive magnesium or magnesium oxide in your data. This is not one of your candidates. But we're going to use this as a sample. Notice that we have the mass of magnesium and the volume of HCl. There's certain data that is given to us, as we said, the density of the solution, the specific heat of this solution. This is the heat capacity of the calorimeter that we had previously calibrated, and we said it was 22 joules per degree Celsius. This is in the example that I gave you earlier. We started at 20.5 degrees and we ended at 38.7 degrees as determined from the graph. So let's go ahead and remind ourselves of how this works. Remember, the total heat that is evolved in this solution is made up of three different things. You have the heat of the reaction, you have the heat exchange of the solution, and then you have the heat exchange of the calorimeter. And we said that according to the law of conservation of energy, everything that happens inside the calorimeter stays in there, so there is no net exchange of heat energy all throughout. So we are going to use this to solve for what is the heat of our reaction, and that'll be minus the heat of the solution plus the heat of the calorimeter. Now let's see what each one of these is. All right, I'm going to try to write it over here. So for the solution, what we're going to have is we're going to have a excuse me, the MCAT formula that we talked about. We're going to have a mass of the solution times the specific heat of the solution times the temperature change for the solution. For the calorimeter, of course, we have the heat capacity of the calorimeter times the temperature change for the calorimeter. Now, we don't have exactly a mass that we measured for the solution. However, we've been given the volume and the density of that solution, so we can use it to calculate what the mass is. So I'm going to put a bunch of numbers in here, all right, so that we can calculate this. I'm going to start over here way on the left so I have enough space. So this is going to be the heat of our reaction. So that'll be minus. Now we're going to put a bunch of things here inside parentheses. So we have the volume of solution, which is 100 milliliters. And then we have the density of the solution, which is 1.050 grams per milliliter, and that will cancel out the milliliters. Notice that this is not water like we used in the calibration of the calorimeter. This solution has a different density. The specific heat of the solution, we said, is 4.9166 joules per grams per degree Celsius. And the temperature change of our solution was final minus initial, 38.7 minus 20.5, and that's going to be degrees Celsius. And if we did things right, here grams will cancel out, degrees Celsius will cancel out. We will end up with units of joules, the units of energy that we're looking for. Now, the other component of this was the heat of the calorimeter. So we established that we had 22 joules per degree Celsius. That's the heat capacity of the calorimeter. The temperature change is the same. In other words, the temperature change happens inside the calorimeter, so we assume that both the calorimeter and the solution ended up at the same final temperature, 38.7 minus 20.5 degrees Celsius. Let's close this big parenthesis here, and we make sure that here, again, degrees Celsius cancels out, and so we are left with joules. Once more, we're going to make all these calculations in here. Right now, I have my calculator in here, but unfortunately, it's not very reliable. So let me tell you what the calculation comes up to be. And I'm going to leave it expressed in regardless of significant figures. I'm sorry, I'm kind of stumbling here a little bit. Remember, this is all going to be negative. All of these numbers here are positive because delta T is positive. It's an exothermic reaction. So everything outside of the reaction is absorbing the heat that's released by the reaction. And so the temperatures rise. Therefore, all these values of energy are going to be positive, but we have a negative there, and it's going to come up to be minus 9796 joules. Again, I am not going to fuzz with sig figs right now. Essentially, most of these numbers are going to have about 2 sig figs. They're going to have to stay simply in the single digits with no decimals. Now remember, this is the heat that is produced by the reaction under these conditions. In other words, by 0.4817 grams of magnesium. The enthalpy of this reaction really is the heat evolved per mole. In this case, per mole of magnesium. So we had to do some conversions here. We had to look up in our periodic table what is the molar mass of magnesium and then do some calculations. So let's see what that is. So delta H, again, I'm going to leave this in my calculator, right, which I had calculated. And that's going to tell me minus 9796 joules. Typically, data for enthalpies are done in kilojoules per mole, so they have to convert this. So we'll say that 1 kilojoule is 1000 joules, and that'll cancel out the joules. And since we want moles, right, we're going to have to divide all this by 0.4817 grams of magnesium. That's what they told us over here. And remember that 1 mole of magnesium is 24.31 grams. Okay, this is, I'm going to write down here magnesium so that you're okay with that. And so the grams of magnesium will cancel out. And we're going to end up with units of kilojoules per mole of magnesium. So let's see what that is. So I had minus 9796 divided by 0.4817 divided by, so 24.31. Oh, I forgot to divide by 1,000 here. So we have minus 494.3756695. These numbers here, and again, I'm going to borrow on the precision that we had for our mass here. And like I said, regardless of what we did, we're going to have about 4 sig figs. So I'm going to let you guys decide back here. I'm going to write down what the final number is, minus 494.4 kilojoules per mole. Now, when you go back and you do these operations here, you'll have a chance to decide how many of these significant digits you keep. But remember, you always have to keep track. Technically, what I think will come up, and again, it depends on the data that you get, you'll probably be able to save about 3 of these significant digits. So this may have to go down to simply minus 494. So I'm going to let you work on that, all right? And that'll be dependent on the data that you received. So I did a very generic approach here. So this would be the delta H of our reaction, the enthalpy of reaction. What does that correspond to? Well, when we did our Hess's law arrangement here, this corresponds to the enthalpy of delta H1, which is reaction number 1. So what you will do now is you will look at the data for the reaction of the metal oxide with HCl. It'll be very similar to this. It'll obviously have a different mass, but everything else will pretty much be the same. Of course, it will have a different initial and final temperature, but the calculations will essentially be the same. Just don't forget that the mass you'll use here, the molar mass, will not be for the metal. It'll be for the metal oxide, so be careful with that. And that will give you the value for delta H2. And once you have delta H2, you also have delta H3. You can get what is the total enthalpy for this reaction, which should correspond to the standard enthalpy of formation of your metal oxide. Now, what you will do after that is you're going to go and you're going to have to look up and find out what is the reported value for this. In other words, you're going to have to find the reported or let's say official value of this enthalpy of formation of your metal oxide. And you can do that, for example, in the appendix of your textbook, or you can simply Google it. And then what you'll do is you will calculate what was your percent error. In your data sheet here in the bottom, it's going to say what is your percent deviation, right? But really, what we're using really more in our curriculum is the word error. So percent error. What is the error when you compare your value of delta HF with the one that's in your either textbook or Google? Or make sure that on your lab report you tell us what was the source for the value that you use as the reported or official enthalpy of formation. Let's go back to our presentation and wrap it up.
Okay, I hope that that was helpful. Again, remember, you're going to receive data sets with different metals, not magnesium. So make sure that you take note of which metal and which metal oxide you are studying. All right. Now, remember that when you assemble your lab report, there are several components to it. First of all, remember, you need to convert the text of the handout into a step-by-step outline form. You then have to put in your calorimeter calibration data sheet along with the 3 graphs, right? And a sample set of how you calculate the specific heat of the calorimeter. You only need to show 1 trial's worth of calculations. Feel free to put all 3 of them in there. And then what is the average? And make sure you complete the bottom part of your data sheet with that data. Then you'll have a data sheet for your reaction of your metal with HCl and your metal oxide with HCl. And you'll have to complete that data sheet. You also have to show 2 graphs, one for the reaction of the metal, one for the reaction of the metal oxide. And then you need to show us at least a sample of your calculations of the delta H of the first reaction, the delta H of the second reaction, and then your final calculation from Hess's law of the enthalpy of formation of the metal oxide according to the data that we give you. And finally, look up the official or reported value of the heat of formation of the metal oxide and show us your calculation for the percent error between your experiment and the reported values. I don't want to leave before thanking Dr. Perot for her very helpful videos, for helping us out with this. And I hope you enjoy this activity. Now, here's the thing. It is a long activity, and please do not wait until the last minute to try to complete it because there are several steps involved and several calculations, and it's sometimes difficult to kind of wrap your mind around what is going on. So make sure you understand the theory, make sure you understand the procedures we carried out and how to analyze them. Go through those sample calculations side by side with your own data, and then please assemble your lab report in a coherent, you know, nice format. Thank you so much. I hope you enjoyed. Be mindful about the deadline, but remember that we always give you a few extra days to finish it if you're not able to meet the deadline. The idea of the deadline is to help you stay on pace and not allow too many things to kind of like crowd your to-do list so that you can enjoy the ride. Okay. Thank you so much. I will see you soon.